One of the first concepts we're going to study is divisibility in the integers, and this is something you know a lot about, but you may not have looked at it formally the way we're about to. So divisibility in the we're going to talk about just the integers. So our definition is a non-zero integer d divides an integer a. What that means to us is that there is this integer k, so that a equals k times d. And the notation for it is this d straight line a. That straight line there would be read divides. So d divides a. Another way you might want to think about it is goes into. So d goes into a is what we mean by d divides a. All right, so we're going to look at a particular example of this and then talk about some other ways you can say this same thing. So 3 divides 12, and we know that based on this definition because there exists an integer k where 12 equals k times 3. And this integer we know is k equals 4. Okay. So we know there is an integer k, so that 12 is k times 3, and we know what integer is. It's 4. Other ways we can talk about this. So 3 divides 12, that fact is not surprising, and in fact we talk about it a lot in different ways. So we have some other terminology. So saying 3 divides 12 is the mathematician's choice of how to talk about this, but you've also probably said 3 is a factor of 12, or 12 is a multiple of 3, or 3 goes into 12, or you might have said 12 is divisible by 3. 3 is a divisor of 12. You might be able to come up with more than this list, but as you can see, there's lots of ways we talk about this same thing, and they all use similar words, but you have to be really careful about it. So the divides and the divisible by are the opposite, notice. So 3 divides 12 means 3 goes into 12. 12 is divisible by 3 means the same thing, but we say it differently. So just try to keep this idea in your head as we go. All right, so a couple of questions with this definition. Let me add a new page here. So a couple of things that are thinking about. The definition specifically said d can't be 0, but can a be 0? So remember our definition was d divides a means a equals k times d for some integer k. Okay, so what if a is 0? Can we complete that equation? So does 0 equal k times d? Yes, this works. For k equals 0 and d can be any non-zero number. And I should be more specific. Non-zero integer is really what I mean here. Okay, so this is a little bit weird, but what that means is, so here's a new notation I forgot to introduce. 3 dots means therefore. So therefore, d divides 0 for any non-zero integer d. Okay, which is a little bit weird. So notice we're not saying I can do d over 0. We're saying that 0 over d is an integer, right? So when we said 3 divides 12, it's because 12 over 3 is an integer. So this straight up and down line divides is not making a fraction d over 0. It's sort of the opposite. It's talking about 0 over d being an integer. All right, one more thing to talk about here. We didn't do an example with negatives, so it's worth talking about how this works for negatives. All right, and this is not too bad once we get used to it. So like, for example, negative 2 divides 8 because 8 is something times -2, where that something is -4, right? Similarly, 2 divides -8 because -8 is something times 2, and that something again is -4. We can also say -2 divides -8 because -8 is something times -2, and that something in this case is 4. So it's fine to use negatives here. We say D can't be 0, but the A can be 0. And that's how this divides works. So we'll be talking about this a bunch. And in fact, the first homework assignment is going to deal with this divides definition. So here is the thing that you're going to be proving. This is lemma, I think it's 1.2 in the book. So the lemma says if D is a non-zero integer that divides A and B, where A and B are integers, then D divides this linear combination. So I'll use that word linear combination in the future. Also, it means I'm taking the two things, A and B, and I'm multiplying by scalars and adding them together. So that's a linear combination of A and B. So D divides this XA plus YB, where X and Y can be any integers you want. All right, so I'm going to ask you to prove this. And this is going to be the first proof of the class. So I want to talk you through what this means to prove this. And then you're going to fill in some of the blanks for homework. All right, so if we want to prove this, it's an if-then statement. And so this isn't the start to the proof. This is just a note for an if-then proof. So an if-then statement. A direct proof would start by assuming the if, the hypothesis. So we're going to start by assuming the if part is true, and then explain why the then part has to be true. Okay, so that's what we mean by a direct proof of a statement. And so our statement, if we go back up and look at it, says if D is a non-zero integer such that D divides A and D divides B, where A and B are integers. And so we're going to start our proof by saying assume D is an integer, D is not 0, A and B are integers, and D divides A and D divides B. Okay, so we get to assume all of that. And our goal now is to show D divides XA plus YB for any X and Y that are integers. Okay, so once we've made our assumption, we assume that that if is true. Now the next thing we're going to do is just talk about what that assumption means. And so D divides A means that there exists a K that's an integer so that A equals K times D. And we can do the same thing with B, right? This time, I don't want to write K again because that would mean that A and B are actually the same thing. So I don't want to reuse K. I want to say there's some integer that might be different. I'll call it L, so that B equals L times D. Okay, so all I'm doing here is using that definition. I'm writing what it means to say D divides A and D divides B. It means those two things. The next thing I'm going to do, I'm trying to work toward that goal of showing D divides XA plus YB. So I'm going to say let X and Y be any integers we want. I don't care what they are. They're integers. Okay, and then I'm going to start looking at XA plus YB and what that equals. So I'm going to do some substitution. I'm going to see if I can come to this using that definition of what it means to say D divides XA plus YB. So I'm going to leave the rest of this for you. I gave you a pretty good start to it, and it shouldn't be too bad from there to finish the lemma. And the language I used is pretty common for proofs, but there are choices you can make. So remember when I said assume up here? I could have also written suppose. If I do, that would be fine. There's lots of different terminology you can use, but feel free to just kind of copy these couple of first sentences and continue on your own.